X depending of u and b, like that, u squared plus u times b, and y depending of u and b also, u cubic times b. And the trick that represents this relationship is c depending of x and y, and x depending ub, and y depending ub also. And the formulas for this specific tree is partial the z with respect to u, for example, is partial the c with respect to x times partial the x with respect to u plus partial the c with respect to y times partial the y with respect to u. And likewise, the CDB is partial the z with respect to x, maybe to keep the same order, you know, and partial the y with respect to u plus partial the z with respect to y times partial the y with respect to b. This is b here, and this is also b here, because the independent variable k considering the second this derivative b, b, u. Okay, so let's compute it by one by one. One by one is partial c with respect x. Here is that expression. It's obvious. It's 3x squared. Okay. So you see some problem, you let me know, right? Partial z with respect to y is similar. It's 3y squared. Now partial x with respect to the u is in this expression is 2u plus b, no? Because b is considered a constant, like a multiplier, you put outside the game, and partial derivative u with respect to itself is 1. And partial x with respect to b is, see, u differentiate with respect to b, u is considered a constant, and this is just u. Because it's considered like a multiplier, go outside, the derivative b with respect to itself is 1. And partial y with respect to u is 3u squared b. And partial y with respect to b is u cubic. Any question in this guy? Any question? No problem. Everyone understand very well this? All right, all good. Okay. Now substitution. So I want in detail, and the test is super detailed. Okay, entonces, who is this guy? Es this. Okay, this. Do you copy? You copy 3 x squared, but who is x? X is this. So the final answer, you need to express it using as a function of the independent variable. Okay, and x and y no, because x and y are intermediate variable. So my final answer is expressed using u and b independent variable in my problem. So it's no x squared anymore. No, is u squared plus ub. Okay, time. Partial derivative x with respect to u is that one. 2u plus b. plus partial derivative z with respect to y is this. Entonces 3 times, pero y square. Who is y? Bueno, y es u cubed b square. One and one extra step. Yeah, this is cosmetic algebra. You foil here, and you apply the property for the exponent. So I did that part. Time partial y with respect to u is 3u square b. Okay. Say, well, I did that here. I is 6u cubed. You just in case you check and see I did well or not. 3u square b plus 6 times u square b plus 3 times ub square plus 9 u9, wow, b square. You check it after that because I underestimate that part. But in the test, no, the test you need to do. You have 1 week, entire week. Remember this test is due and the online also next Monday. Actually, I grade next Tuesday. Huh? Okay. And now the second. It's the same. It's just substitution and that's it. But let's do it. Partial z with respect to x. Partial z with respect to x. So that guy. I did that. It's 3 times u square plus ub, no? But it's a square, no? It's a square. I make a mistake here, right? It's a square. Oh, yes. Okay, no, this is wrong. Okay, this is wrong, I suppose. Okay, this is a square, no? Here. Because it's x and x is this. Okay. So it's a square. It's more complicated. I need to expand this multiplication. Time. What is partial y with respect to b? U. Plus partial z with respect to y is this guy, no? It's 3. And y is, this was similar. U cubed b square. Time partial y with respect to b is u cubed. Okay. So do you understand? Okay, the rest is algebra. Because if we are doing in detail here, we lost time. Now you are doing. This is piece of cake for us. We are advanced students, no, mathematicians here. You have no problem with this. Okay? Any question? Any question? No? No? Let's move on to the next question. Question 6. No problem, guys. Sure. I want to erase the board. I can. Answer me. Yes, no. No question, no?
Clear.
Chain rule. Oh, clear. Okay. Chain rule is easy. Now, okay, good. Number 6 is about the implicit differentiation. Let's give it this expression, 2x squared plus 3y squared plus 4c squared equal 5x times y times. Well, the only thing it should do is express it in implicit form. And implicit form is exactly the same. The only thing is the right hand side is 0. If you want to find the formula is minus capital F. Remember, this is capital F. This is capital F, que depending of X, Y, and Z. Divided by partial derivative of the capital F, que is the implicit formula, implicit form, differentiate with respect to X. It's doing. Here, partial Z with respect to Y is equal minus capital F with respect to Y divided by F with respect to Z. Okay, so we need to basically compute it three partial derivatives. Fx, Fy, and Fz. Okay. Fx, I come back at the original no. The equation in implicit form, and you differentiate with respect to X. Es obvio que es 4x minus 5 yz. Boom. Cool. Because the only term que contiene X is the first and the last. And the other no, se considera constant. No? Likewise, Fy is equal 6y minus 5xz. And Fc is az, that guy, minus 5xy. And the rest is easy. Just plugging in the formula and end the story. The partial derivative z with respect to x is equal minus. I copy the expression que is 4x minus 5yc divided by az minus 5xy. There are many ways to write that. So this is fantastic. It's good, no problem. Another way is suppose that this negative you believe is in the top. You put in the top. So change the sign 5yz minus 4x divided by az minus 5xy, or you suppose that this negative in the front, you put in the bottom. So it's 4x minus 5yz divided by, in this case, I change the sign 5xy minus az. This is one possibility. Either way, this is algebraically equivalent. No calculus, is just elementary algebra, and that's it. And suppose another is minus, entonces fy, this is y, sorry, it's a y. Let's see with respect to y. Fy is that one, 6y minus 5xz divided by fc is az minus 5xy. Likewise, in this case, you can interpret the negative in the top and the bottom. Either way, I don't want to copy because this is easy. Any question?
Professor, what is the question that they're asking for this?
What is the question of what?
Like what on a test? What would the question like say?
Well, you say differentiate. Find, for example, partial y with respect to x, and you see in the expression that's given in the problem is implicit. So we cannot isolate, for example, the y. Entonces you immediately you understand that you need to apply the implicit differentiation formula. And the difference between Cal 1 and Cal 3 is in Cal 3 we are doing more systematically because we have the formula, no? So you immediately compute the partial derivative associated with the problem, and division and change the sign, minus in the front. End the story. So and you can differentiate any function, multivariable, and you can find any partial derivative or not necessary partial derivative. I suppose in the test we have one problem, que is no Cal 3, it's Cal 1, but it's weird. The solving using Cal 1 is a little bit complicated. However, using Cal 3 and the formula for the implicit differentiation is easy. Entonces, in this case, I ask you in the test, compute dy dx, but we cannot algebraically isolate the y in this equation. Entonces, you apply the implicit differentiation. More clear this idea? This was exactly you asked me or no?
Yeah, that's what I was trying to ask. But so those are the only two formulas for implicit differentiation?
No, not do infinity formula, because you for example, you need to find partial something with respect to something. The formula say is f of something divided by f of something. It doesn't matter who is with a square or circle. This is the formula.
Okay.
Okay. Any other question, guys? Clear? Implicit differentiation. This is super easy. Don't try to see beyond the thing you. But this is super powerful with respect to Cal 1. Okay, 7. Question 7 is a typical max mean without constraint. No constraint. So one function is given that represents one surface in 3 dimensions. I have no idea what the name of this surface because it's completely weird, cubic. But this is not important now. And you need to find the max mean, okay, using the idea. And the domain is R2, so the completely plane xy. Okay, step 1, you compute the partial derivative with respect to x. Well, actually, you know the max mean and the function you obtain in the peak of the hill or in the bottom of the valley. In this case, the gradient is 0. The gradient is 0. Remember why the gradient is 0? Because the gradient indicates the direction, the steepest ascending or steepest descending of any function in 3 dimensions. As you go exactly to the peak of the hill, it's obvious that the gradient disappears because there are no direction to increase it more. Okay, suppose you compare the gradient here. Oh, no. So the gradient is in this direction, will indicate that you're moving in that direction to reach the peak of the hill, no? And the valley is completely different, as you point in opposite direction. Okay, so now in a few words, not necessarily talking about, you compare both partial derivative and you enforce it to be 0. And this is my critical value. And to testing this critical value, you apply the second derivative test, is a little bit more complicated than calculus 1. Okay, so the partial derivative, the function with respect to x is 3x squared y plus 24, and you enforce 24x, and you enforce it to be 0. Okay. And partial derivative f with respect to y is x cubed minus 8 equals 0. In this moment, we have a system of equations, non-linear of course. And you solve it using your imagination or putting Wolfram alpha, but in this case, no big deal. Okay, and then you, for example, you take the equation, this is equation 1, this is equation 2. If you take the equation 2, it's obvious that x is 2, no? Because you Put a to the other side, apply cubic root both sides. X is 2. At least 2 is the solution for this equation real. Of course, we have 2 more solutions because the degree is 3. But this is imaginary. Imaginary do not participate in this game. Now, in order to find the y associated with these 2, why are you plugging in the original equation maybe? Oh no, or plugging in the second equation, no? It's 3, because actually we finished to solve the system, no? Entonces 3 times 2 squared is 4, y plus 24 times 2, no? Equal to 0. This is 12y plus 48 equal to 0. 12y equal minus 48 divided by 12 both sides by 4, negative 4. Entonces, the thing that we discover is that the point 2, negative 4 is a critical point. Critical point. To determine the nature of this critical point, we apply the second derivative test. Remember, in a multivariable, we have a famous local max, local mean, or saddle point. Remember, local max is when the both second derivative is concave up. Suppose another derivative is this. This is, sorry for my 3-dimension sketch, it's no good. See, the both second derivative point up is mean, local mean. And see, point down is local max. However, see, one point upward, another downward is saddle point. Okay? So let's compute the second derivative. It's no big deal, it's easy. Let's compute the second derivative with respect to the x 2 times. And the second derivative, you take this expression and differentiate with respect to x as 6xy plus 24. Done. And now you differentiate the function, the surface with respect to y, second derivative. Okay, is 0. Wow, it's 0 because this expression do not depend on y. Okay, nice, nice. I like that. 0 is good. Simplify our problem. And partial derivative f with respect, for example, with respect to x first and y second, no? Okay, by the way, it's exactly the same partial derivative f with respect to y first and the second. Let's do it either way. Is suppose que I did that. Is okay, you take this expression for example. Oh no, either way, you take the easy. What's the easy? The easy is this. I did the derivative, the partial derivative with respect to y. Now I differentiate with respect to x. Okay, it's 3x squared. This is clear. Now I need to compute the famous discriminant, que is capital D. Capital D evaluate at the point 2, negative 4. Que is my critical point because the reason que I'm doing this is because I want to understand the behavior of this. Entonces es plugging in. You can plug it in directly one by one here. It's 6 times 2 times negative 4 plus 24, no? This is negative 24, no? This is negative 24, yeah. It's negative 24. Remember, the formula is fxx evaluate at the point 2, negative 4 multiplication by fyy evaluate at the point 2, negative 4 minus this guy fxy or yx in the square, evaluate the point 2, -4. Entonces, the answer of this was -24, no? Yeah. The answer of this, wow, is 0. Because the second derivative is 0, no depending on x and y. And that part disappears. And that part is, let me try, it's easy. Because it's 3x squared, it's 3, 2 squared, is 4 is 12, no? It's 12. And 12 squared, 144. And don't forget that negative. So the answer here is negative 144. Conclusion, guys. Conclusion, when the discriminant is negative, yeah, definitely, you don't need to investigate anymore. This is saddle point. So at this point, the only point critical that we have in this surface is saddle point. End of story. Super. Any question? Guys, I need to understand, I need to know, can you follow me? I try to explain super clear. Well, in my opinion, in my opinion, no? It's in my opinion. So when the one thing is good or is bad is completely relative, depending, no? The thing is good for me, maybe it's not good for you. So we are a team, try to do something, que the something is learn, calculus 3, then entonces you let me know si I'm doing too fast, I'm doing no good, you need to one extra explanation because the test is completely independent, it's for you. I cannot help. Okay, the question A say.
Professor?
Go ahead.
What was so there was no local max or global max, there was just a saddle point?
Yeah, this surface only have saddle point. It's obvious. For example, the famous hyperboloid parabolic. You know that the shape is like the seat of the horse. When you sit on the horse, have no max min. It's only saddle point.
Okay.
So yeah, it's crazy. And I illustrate in the lecture now one weird surface. Okay, this surface have min, max, and saddle, two saddle. Pero no, this is totally, randomly. Not randomly, but it's depending on the surface. Okay, the question A, que es el most, not complicated, pero es the part que I feel que some students don't understand very well, is find the global max and global min. So in this case, we have an also surface, que is 1 plus 4x minus 5y. And we have a specific region, in this case is a triangle. So we have a vertex, que is the point 0, 0. We have another here, 1, 2, 2, 0. And we have another here, que is 3. 1, 2, 3, 0, 3. And we have the triangle. And this is my region. I need to investigate everything. I need to investigate if the gradient of the surface equal to 0 produce critical value, and I investigate the nature, but no using the second derivative. Remember, because it's the problem of the global. So not necessarily they are perfect coincidence in between local max or local mean and the extreme value. But this is the glue. See, the critical point lie outside, I don't care. See, lie inside, I care, right? Okay, this is my first problem. The second problem que I feel que some students don't understand very well is that we need to navigate for the boundary. But the boundary is one dimension. This line, que by the way, this line is, let me call, no sé, path 1 is y equals 0. So when you're moving throughout or through the x-axis, it's obvious at any point the y is 0. When you're moving, for example, for the path 3, look like more complicated, because in this case I need to investigate the equation of that line, but it's super easy for us. So path 2, no? Path 2, yeah, path 2 is a line. Okay, I need to investigate the equation of this line, and only to convert my problem of two variables, x and y, and only one variable. So don't forget the corner, and don't forget one potential local mean or local maximum on this boundary. And finally, the path 3 is on the y-axis. Okay, obviously on the y-axis is x equals 0. This is easy to determine this. This is a little bit more, no hard, but it's a little bit more complicated because I need to find the equation of this. But let's do it step by step. Okay, first of all, I have no idea. So I computed the partial derivative with respect to x, so the gradient 0. Entonces es, partial derivative is 1, es 4. It's 4. F4. Yes. F4. And partial derivative with respect to y is -5, no? And entonces now the idea for the local max mean is to put it 0. Pero equal to 0 maybe is a contradiction because 4 and -5. That means that we have no critical value. And make sense, guys. Why? Because this surface that we are working is super easy. It's a plane. You see it's a plane, right? Remember the typical equation for the plane, que is ax squared, no square, ax plus by plus cz equal d. Entonces you have x, you have y, c is this, so f of x is equal to c. It's a plane, you see que es línea, es flat. Entonces si es flat, we have no peak of the hill, we have nothing. Entonces now no critical value. Okay, nice. Entonces I focus 100% to navigate from the path. Path number 1 is y0. And substitution in the formula, in the surface, x, 0. Entonces es 1 plus 4x. Cool? 1 plus 4x because y is 0. Yeah, I like that way. I don't know if you like. This is my way, no? Called function 1 because corresponding with the path 1. Entonces now, if you differentiate, cal 1, this is only one single variable problem. The answer is 4, and 4, no 0. Again, when you travel with this, we have no critical value. Now, entonces I evaluate only in that corner. You evaluate, if you want, you evaluate the function 1 and 0. Es obvio que es 1, no? You can evaluate in the original, but you can evaluate here also, because actually in this path I did y equals 0, so either way. And f evaluate in 2 is 4. It's 4. It's 9. It's 9 because 4 times 2 is 8 plus 1 is 9. Okay, if you want, you put the label put the label, that label can indicate C equal 1. Because you don't see the problem in 3 dimensions. The 3 dimensions, the C component is completely one axis out perpendicular to the whiteboard. In this point, we have C equal 9. In the middle, I guarantee you this statement 100%, because we have no peak of the hill and we have no valley. No. This is completely linear. Okay, this is the path 1. Everyone follow me? You can navigate for the blue or for the red. Let's do it. Suppose I don't know anything. Path 2. On path 2, I need to find the equation of this green line. And the slope of this equation is the famous formula guy y2 minus y1 divided by x2 minus s1. You take the point 1 and 2, this and this, no? Is 3 minus 0 divided by 0 minus 2. Is negative 3/2. Makes sense que it's a slow negative because it's going down from left to right. I'm using the famous equation y minus y1 equals slope x minus x1, que is a point slope. Okay, in my opinion, it's a fantastic way to find the equation of any line when you have in your hand slope and 1 point. So the point I take totally arbitrary. I take 0,3 or 2,0. I take in my paper 2,0. So I suppose que y minus 0, because I take this point, is equal minus 3/2 parenthesis x minus 2. Okay, therefore y alone is equal, distributive property here is minus 3/2 x plus 3. Okay, and this is the equation of our surface. Now, what should I do? Well, si you declare que this expression or equation represent this path number 2 in green color, when you evaluate in my surface, que by the way is a plane, que es nice, that is the reason que es nice, 1 plus 4x, and you replace minus 5. So instead of y, you put this, que es minus 3/2 x plus 3. Cool? So now I call function 2 depending of x only. Okay, entonces f2, que depending of x only, is 1 plus 4x plus 15 over 2x minus 15. Therefore, f2 and x is equal 23 over 2x minus 14. When you differentiate with respect to x, in order to find one hypothetical critical value here, well, is 23 over 2. Okay, one more time happen que no 0. Similar situation of this. This is a similar situation. Okay, but I found the corner, that corner and that corner. Es F2 evaluate en 2. So that one evaluate in 2. Is 23, is 9. It's logical. I did before. Look, this corner is exactly this corner. I don't realize this, but when I see, wow, 9 sound familiar. But it's logical, it's the same corner, it's the same surface. And F2 evaluate in 0 is, let me see, is negative 14. I put the label here. The C value and this corner is -40. Okay, now why not? To make sure everything is clear, I travel for the path 3. The path 3 is super easy. Path 3 is under the supposition that x is 0. Therefore, our function is f0, y would be 1 minus 5y. I call f3, que depending on y. Okay, when you differentiate, it's -5. And -5 no 0, no critical value. And this conclusion, guys, is expecting at the beginning because my surface is a plane. I promise in the test, no. In the test, the surface no plane. That you need to working carefully, step by step, any path, and you discover something in the middle of the path. I put this example trivial in the review because I don't want to waste too much time doing this. And you evaluate the FN3, you evaluate where? Well, you evaluate in 0, FN3. And evaluate in 3, N3. It's logical. It's logical. Okay, we have exactly the same value again because it's a triangle. A 1 and -40. Okay, super. So not necessarily make a list in this case. And the test, yes, you need to make a list because you discover in the middle here something when you find the first derivative. And so one of my list actually is Fn00 is 1, Fn2,0 the list. Important to see the list, guy. Remember, it's typical problem of the optimizations, max mean, pero global. Entonces, you don't apply second derivative test. No. You compute the critical, pero compute its value. Es 9. It's 9. It's 9. And Fn2 is 9. Yeah. Y Fn 0,3, ¿no? Que es -40. Obviously, this is the global max of our surface. Is the global mean. End of story. I finish. Super easy. I told you. It's super easy. Yes or no? I told you. It's easy. This is nothing for us. I know que es too long. So we have one entire week for doing slow down, okay, double checking for everything. Guys, it's important because I understand everyone, even me, make a mistake. No conceptual mistake, it's an algebra mistake. I forgot the word negative. And so you make a mistake. Of course, this mistake, the problem is when you drag this mistake, so you get the wrong conclusion, and then entonces sound no good this question. So my recommendation is using software to double checking everything, right? Double checking. Let's practice a little bit software. Let's practice a little bit, and entonces you help me. Any question in the question number 8? No problema.
Professor,
No problema.
Since there was no critical value,
Well,
if there was a critical value, we'd also have to put that on the list, right?
say again. See, you have critical value. What you say?
We'd have to put that on the list as well.
Absolutely. And the list ending. Look, listen to me. Ending. The collection of the critical value that you compute when you enforcing the gradient equal to 0. Put in the list. Okay, maybe it's not necessarily one solution, maybe it's 2 solutions to critical value. But similar to are doing the optimization problem without constraints. plus the corner of the region plus the intermediate value in which is also critical. Okay? When you apply, when you enforce the restriction of the path in the original surface, you obtain a new function that I call f1, f2, f3, que is only one single variable. And one more time, you apply first derivative, you determine the value of this, and you include this new point into the list. Suppose que I change, suppose que I change the surface, no plane. I put, for example, a square here. Wow, that's changed completely the problem. I guarantee you that when you compute the derivative path by path, you get a new critical value. And you don't check if it's minimum, maximum, I don't care. You include in the list and you evaluate everything in the original function. Bam. So now this is a crucial moment and you make the decision. What is the greatest value? Bam. Global max. What is the smallest value? Bam. This is global mean. Cool?
Clear.
Okay. Erase the board. Let's move on to the next question. So, in the review, I put a lot of problems of the Lagrange multiplier. I don't know if I need to do everything because too much. Let's do at least a couple. No, I don't know. The first say, okay, you have the function. Is, well, the function no. You have you have function que es xy. The problem is in 2 dimensions. And we have also, we need to find, let me read exactly what is the question in the review. Okay, let's say, find a point in the curve x times y equal 1 that is closer to the origin. We use the Lagrange multiplier. Okay, I understand. Okay, the idea is, this is a function in 2 dimensions, the reciprocal, the famous reciprocal function, equal 1. Sorry, this is not f of x. This is equal 1. Okay, y equal 1 over x. Call it algebra. Reciprocal function. They need to investigate what is the point on this or this branch. It doesn't matter. It's close to the origin. So I need to minimize that distance because close is minimum distance. Okay? Okay, just remember in any problem of the Lagrange multiply format, we have two functions. Objectives function is the function that you want to minimize or maximize. It's the function that you want to optimize. In this case, the distance, no? I need to guarantee the distance is minimum. And we have constraints. In this case, only one. Okay, so now the function, I need to create my own function, get distance. No? Distance equal square root. So in this case, 0,0. And this is completely arbitrary because I have no idea. Well, I have some idea because using my intuition, I suppose that this is closer, no? Because this is go or weight to the origin. But okay, mathematical, I want to prove, no geometric. Entonces es x minus 0 and y minus 0. Es obvio que this is a function. This is the objective function. I need to guarantee that this is minimum. Mean. Cool. As always happen, well, I don't like the square roots. So I want to optimize the function. I want to call f of x comma y in the language of the Lagrange multiplier. This is f of x comma y. In the language of the Lagrange multiplier, this is g, x comma y equals 0. This is a typical format for the Lagrange multiplier. So in order to don't complicate my life, you optimize not this, you optimize d squared. I call f of x comma y, que es x squared plus y. Okay. This is like a smart way, no? We can do that in that way, of course, but the derivative is complicated and complicate the algebra of the system of equation. And what is the constraint? The constraint is this constraint. Look, it's a function is given, right? Because subject to this function or another function. Entonces, en Lagrange multiplier language, x comma y is equal 0, ¿no? Es x times y minus 1 equals 0. Boom. And this is my Lagrange condition. Pero Lagrange working with the gradient. I need to compute the gradient of f. Should be equal lambda. The lambda is the Lagrange multiplier. It's a number que I don't care. It's a number que participate in the game. However, it's not important because it's when the gradients are parallel. Okay, no problem. Entonces, I propose you create the systematic way. For example, you compute the partial derivative f with respect to x. You compare the partial derivative y, f with respect to y. You compare the partial derivative g with respect to x, and you compare the partial derivative g with respect to y. It's the component of the gradient, no? Both gradient. Partial derivative f with respect to x is 2x. Super easy. Partial derivative g with respect to x and y, ¿no? Eso, ¿no? Equal, you consider que x, y is a constant, 1, negative 1 is obvious que es constant, entonces stay alive only. You differentiate x with respect to x is 1, entonces y. Likewise, this is x. Entonces my system, remember the system, o sea, this statement expressed component by component in Lagrange multiply equation, system of equation is f in x is equal lambda g in x. Equation number 1. F in y is equal lambda g in y. Equation number 2. And we need one more equation because you introduce in this Lagrange multiply game, you introduce lambda. Then you have x, y, and lambda, 3 unknown. So in order to complete the system, you introduce the g x comma y equals 0. And the equation number 3, specifically, this idea in our problem is 2x is equal lambda y. Equation number 1. 2y equal lambda x. Equation number 2. And the last equation is x, y. You write like that, equal to 0, or like that. I don't know why I prefer in this way. Equal. I don't know. There's no reason. That's my mind working in this. Okay, so we focus in this part. Let's do it by hand. Let's double checking with the Wolfram alpha. And those the next problem you help me with the Wolfram alpha. So I recommend, no, now, let's do it by hand now. By hand is super easy. In this example, some examples is crazy. It's crazy, entonces, pero this is just algebra, no calculus. Entonces, I skip this algebra. But in this case, you divide equation number 1 divided by equation number 2. because this is frequently doing, in order to eliminate the lambda is no important. So you divide, when you divide, you have 2x divided by 2y is equal lambda y divided by lambda x. Entonces es obvio que 2 es cancel, lambda is cancel, x over y equal y over x, cross multiply, and you get y squared equal x squared, and y is equal x, maybe plus or minus, right? But it's okay. I keep in mind it's plus or minus. And substitution in the third equation. And the third equation is xy equal 1. But I know that x and y is the same. So it's x times x squared equal 1. Apply square root both sides. Now I consider plus or minus. Entonces, y es igual. Entonces, plus or minus. Entonces, I identify the maximum and minimum, of course, global, because we are talking about constraints, occur at the point +1 and -1. In order to identify who is maximum and minimum, you plug in this point in the original equation. And the original equation that I want to optimize is d equal square root x squared plus y squared, ¿no? Entonces now it's obvious that use substitution, everything I can do. So basically we have 4 combinations, no? We have 1, 1, -1, 1, 1, -1, and -1, -1. Okay. Entonces es when you substitution, doesn't matter the sign, plus or minus y squared and plus or minus square. I do simultaneously because you know when it's a square it's positive, is 1 plus 1 get 2, and the answer is radical 2. But this answer and this answer have no sense, because remember our hyperbola exists in the first quadrant, in the third quadrant, not in the second quadrant, and fourth quadrant. Okay, so this is expecting the famous point is close, is the point 1, 1, and -1, -1, and this distance is radical 2. Boom, final answer. It's obvious, expecting, it's the famous triangle 1, 1, radical 2. Okay, you know very well in geometry. Okay? Okay?
Professor? What was the goal of the question? Like, what were we supposed to find?
Say again?
What were we supposed to find?
What?
What were we supposed to find?
I suppose you find the point in which on the curve xy equal 1 is closest to the origin. Okay, so you, for example, you have the famous hyperbola, this, and you travel here and here, and you need to find when this point is close to the origin. This is the idea. Okay, let me read again the question, mister. The question says, find the points on the curve x times y equal 1 that is closest to the origin using Lagrange multiplying method. Clear?
Clear.
Okay, let's practice Wolfram alpha. Wolfram alpha, I propose that everyone open in your laptop, minimize everything, no close everything, only minimize. I minimize. Okay, and I open another browser. Okay, you put Wolfram Alpha in the keyboard, Wolfram. Guys, you need to be familiar with this because in next chapter we use it every day, Wolfram Alpha. But in this case, no calculus, it's algebra. Okay, let me share the screen. Share, screen, Wolfram Alpha. Do you see Wolfram Alpha in your computer now? Oh no, mine. Okay, if you want, well, you open in your computer also, no? But well, you see my process first, and after you try, because the next problem I would like you solve for me. I am boring to do this. So you, for example, ready? Everyone is ready to pay attention. Do you see very well my Wolfram Alpha? No, your old Wolfram Alpha. Do you see yes or no? Come on, answer me. Hello, what happened? What's going on? Do you hear me or not? Okay. My question was, do you see Wolfram Alpha?
Yes.
Cool. See. Okay, you click in algebra. You select any. Well, no, any box that contain the word solve because so much. Here I did. I erase everything. The word solve. See, you open and you type a solve. This is completely independent, and you type in the equation. Entonces now we have no lambda. We have to say I replace lambda for capital L. Entonces you put 2x, solve the system. 2x. And between number and variable, not necessarily put time symbol because default Wolfram Alpha understand is time. But in between two variables, for example, capital L, que es lambda, time, y. So you put L and y together without time, Wolfram Alpha believe que L, y is a new variable. Entonces now don't understand the problem, your problem. Put a space, you put and you connect the several equations, 2 equations, 3 equations, 4 equations. Let's do it. 2y equal capital L times x. And the last one, que es x, pero the same, no capital X. X times y equal 1. And either way, in implicit or in explicit. Sorry. Equal. Do you follow me? Okay, the rest is click in the button here. This button, compute input. Wait a few seconds. Entonces now Wolfram Alpha is nice. Summarize important the information for the system to verify if we copy well or not. See, to verify if Wolfram Alpha understand very well our system. Give me que lambda es 2, pero 2 are negative 2, pero negative 2 produce imaginary. That is logical because it's a supposed solution in the second quadrant and in the fourth quadrant. No. In the real field, no. In the real field, we have solution in the first quadrant, que es 1,1, and in the second quadrant, que es negative 1, negative 1, no? And the L is 2 because L, you suppose, well, I don't suppose anything. And now, if you want to determine what is minimum, what is maximum, in this case, both are minimum because it's a closed distance. Make sense? Any question? Any question? No, so far. Okay, let's move on again to the whiteboard. Boom, boom, boom. Okay. My intention today is at least start the chapter, new chapter. I don't know if we have time. I propose you do one more example of the Lagrange multiply. And that's it. The question 10, the rest is similar. The rest is similar. Is the 10 questions talking about John. John is a guy who wants to build a 500 feet desk behind his house. What dimension of the deck will minimize the length? Okay. So I don't understand anything. I do the sketch. This is the John house. And they need to find one, I don't know, it's this portion here. And the area includes a 500 feet, square feet. And the dimension, I have no idea. This is a challenge I optimize. Is, suppose I call x, y, y. Because it's a rectangle, no? And this rectangle have only 3 sides. Okay, so now the function, the objective function that I need to minimize in that case is the material, no? It's a perimeter, no? Perimeter is minimum. And the perimeter is obvious que es x plus 2y. I need to minimize. Min. No, m. Minimize. Okay. This is the objective function. Okay, in language of the Lagrange multiply, I call fx comma y is equal x plus 2y. Cool? Entonces, what is the restriction? Well, the restriction is the super 500 square feet. I need to respect this restriction. The restriction is que the area is 500. And area in geometry, you know very well, is x times y. Expressed in Lagrange multiply language, this is x times y minus 500 is equal to 0. And this is the setup for my problem in Lagrange multiply language. That's all we happen. We compute the gradient, component by component. You compute, for example, fx, fy. And you compute it g, x, gy. Well, this is 1. It's obvious. Derivative of this with respect to x is 1. And derivative of this with respect to the y is 2. And this derivative of this with respect to the x, sorry, is y. And this with respect to the y is x. Okay, so my system of equation is super easy. 1 is equal lambda y, equation number 1. The second is 2 is equal lambda x, equation number 2. And x times y is equal 500, equation number 3, is the constraint. Express like implicit or not. Personally, I like this way. Okay. And the solution here is similar to the other problem. You divide the equation 1 divided by equation 2. This is frequently happen because lambda I don't care. So 1/2 is equal y over x plus multiply x is equal to y. I'm plugging in the third equation. 2y times another y gets y squared equal 500 divided by 2, y squared is equal 500 divided by 2 is 250. This is square root of 50. Square root of 50 is 5 radical 10. Because 250 is 25 times 10 and the square root of 25 5. Well, entonces x es twice 2 times y, entonces 10 radical 10. Okay. This is the dimension of the perimeter, que es the function that I want to minimize, is 2y. 2y, so multiplication by 2 is 10, 10, 10, 10, radical 10, no? Okay, multiplication by 2 here, plus 10 radical 10 is 20. Radical 10. And this is approximate to have shown geometry idea how many material we need to construct this is 63.725 approximately, you know, 25 linear feet, no? Because it's perimeter, no? It's material of the, I don't know si es concrete, aluminum, wood, I don't know exactly what material you want to build this. This idea is clear?
Perfect. How do you know that you minimized it and you didn't maximize?
It's okay. Okay, good question. Good question. Excellent question. One possibility is you try one couple of value close to the x and y and plugging in, okay, and plugging in into the perimeter function and verify, see this, you suppose you put 5 radical 10, convert to the decimal, 10 radical 10, convert to decimal, and you trunc it, for example, the decimal part, and plug it in the perimeter. See the answer is bigger. That means que the Lagrange multiplier solution is minimum. Pero another possibility extra que I did in my paper. Your question is perfect, Mister. You are David, no?
No, Max.
Math. Okay. Maximilian, no?
See?
Yeah. Another thing I did in my paper to verify this, you saying this is the optimization problem exactly the same we are doing in Cal 1, guys. Look, suppose y equal 500x. This is the function, right? However, the perimeter is x plus 2 times y, que is 1000 over x. Makes sense, right? So the thing I did was I take in the constraints, isolate the y, I plug it in here, 500 multiplied by 2 is 1000, and you apply Cal 1, dp dx, dp, no partial, ordinary, and Cal 1, I don't know anything about ordinary derivative. Well, derivative, this is 1, and this is, let me change different to make sure que yo apply the power rule, ¿no? Entonces es minus 1000 x to the minus 2, something like that, equal to 0, equal to 0, equal to 0. Entonces equal to 0 is, I solve this equation. Entonces this equation is 1 equal 1000 so over x squared, something like that, right? I moved. Now. So for x, cross multiply x squared is equal 1000. Apply square root both sides. X is equal 10 radical 10. Because 1000 is 100 times 10. And 100 square root is 10. And we get the same answer. But, Maximilian, the thing I want to illustrate, for everyone, is in order to find si es mínimo o es máximo, you apply the second derivative test of the function que I expect to optimize. And the second derivative, I differentiate this expression again. Derivative 1 is 0, and derivative this is positive 2000 x to the minus 3, right? Okay, and or it's equivalent to say 2000 x cubed, you know? And now I substitution that value here. And you raise to the cubic power, but it's not important. No, I don't care to do this. The value is not important. The sign is important. The sign is positive. It's obvious, right? If it's positive, it's a minimum. Because this curve is concave down. Down, no. Up. Because it's positive. Concavity, positive, it's like that. This is minimum. More clear now?
Yeah, so we could have solved this using methods from Calc 1.
No. This is powerful than Calc 1. This is good. And this case was a particular example. Okay, I could do by Calc 1 because it's extremely easy. But suppose you have, I don't know, in rocket science, you have 10 variables. Yeah, I want to optimize something, one device. Entonces you apply Lagrange multiply. Oh, it's obvious, right? Lagrange multiply is powerful than Calc 1. Okay?
Yes.
I propose you, in order to save time, I propose you one idea. One idea. It's a challenge. The problem 11, 12, 13, and 14 is the same stupid thing. Es Lagrange multiply. Y I can consider like extra credit. 2 points for each. So 1, 2, 3, and 4 extra credit. Well, it's completely legal, no illegal. Because you stop doing this problem, you ask me, okay, by email, professor. Entonces I don't solve it full for you, sino es no extra credit. But I solving something, I push you to continue, go ahead, right? Okay. I don't know. This is my idea. What do you think? It's good or no?
Is that for just the extra credit questions?
Yeah. You consider like instead of the traditional 10 questions, you consider your test. No. It's different concept. It's extra. Si es extra, es a fixed point. It's 2 points. So we have 4 questions, 2.8 extra point. Okay?
And that's going to be separate from the 10?
No, you send me together. Together. I understand que es extra, right?
Mm-hmm. But you can't help us on the 10 that you sent us first.
A little bit. Not too much because, it's not funny, no? It's extra point. I give you point, reward. Yeah, I help you, no? Hello. But also, yeah. I can, so you are stuck to interpretation something, I can clarify this.
Even if it's one of the 10 that is like the real exam.
10 regular question and 4 extra credit. Do you understand very well or no?
Yes.
Excellent. I want to start a little bit the new chapter. The new chapter is amazing. It's my favorite chapter. It's about a multivariable integral. It's an introduction. Today we're talking about introduction. Introduction to multivariable integral. And we study, I guarantee you, we study double integral and triple integral. So in general, we can do the traditional way, integral, antiderivative, or define integral using limited. We study double integral and triple integral, que es the most popular application in science and engineering. In general, we can apply multiple integral, four integral, but no, have no sense, physical sense. Entonces, this is super, so I need to dedicate my time to explain the meaning. So you need to understand the thing you will compute. It's important. Your question, Maximilian, is important because you need to understand what you're doing. Okay? The meaning of this double integral. What is that? What is the meaning of the triple integral? What is that? I don't understand. Okay? And of course, the algorithm to computation, this multiple integral. Entonces, for example, in Cal 1, we study the one integral, define integral. Let's see, I ask you, what is the meaning of this integral? I suppose 99% or 100% of the students say area under the curve. Yes or no? Area under the curve. Because the teacher explained this, explained 3,000 examples of the area under the curve. However, this answer is not 100% true, because the teacher in Cal 2, I suppose, explained another application of the integral, que is, for example, r length, surface area, volume of the revoluting solid. Entonces, really, the answer is, what is the meaning of the integral? Well, depending of the nature of the integral function. See, the nature of the integral function is just f of x, is obvious, it's area. However, if you square this function and multiply by pi, you know very well that is the volume of the one solid that rotate around the x-axis, no? Or, for example, integral square root 1 plus derivative this square dx between a and b. This is the r length of the curve in between the point A and the point B. Okay, so now, what is the correct answer? What is the correct answer? What is the interpretation of the integral? Well, the interpretation to understand when I increasing the dimension in Cal 3 is the Riemann sum. I want to refresh your memory because some teachers underestimate this idea of the Riemann sum and dedicate not too much time for doing this. Okay, I don't want to dedicate too much time, but at least to see the view of this. What is the idea of the Riemann sum? In Cal 1, I want to extending, I don't know if we have time today or no, to multivariable. The idea behind Riemann sum is you have a function, y equal f of x. You need to compute it in one specific interval, a and b. Okay, and you make a partition. So this is my interval. Okay, by the way, it's one dimension. It's a segment. You are doing the partition. You declare, for example, delta x is b minus a divided by m, because you are doing m partition. Bam, 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 bam. Not necessarily equal sign. In this case, using that formula, yes, it's equal sign. Okay, cool. And you take, for example, in one arbitrary partition, you take one value in the middle. The teacher, I suppose, can explain using the right endpoint, using the left endpoint, and using the midpoint. And because when you compute the integral using numerical method, you're using this traditional way. Or another method. But this is not important. The important is you take arbitrary value, okay, called x after, because it's completely crazy, arbitrary, and you take the high of this. So this is f evaluating x after. Suppose that in this interval I take one in the middle and another take in the left and the right. We are doing Riemann Sum in 3D. Of course, David. Of course, David. This is the idea I try to convey today. So it's the same thing. I want to illustrate, but very well with the animation. You see how you move in the Riemann Sum. But I suppose that we have no time today. Okay, so the idea is the U multiplication f and x after I because I take the I partition 1, 2, 3, 4, 5. I take the partition number 30 after multiplied by delta x. I put delta x or delta xi, either way. Dependency of the partition is regular, so I'm using the same common delta x or no. So I'm doing crazy partition. I guarantee you 100% that the integral converges to the same value. It's completely regardless the selection of the point and the selection for the partition. And summation, everything. Okay, from I equal 1 to m. This is a Riemann Sum. And apply the limit when the delta xi approaches to 0. So I put a small partition, or another way, not both, when the n approaches to infinity. Magically, this is magic. This is science fiction. This Riemann Sum change to the integral. Okay? Wow. This is the idea. Riemann Sum. The fundamental theorem of calculus, the computation of that part is super easy, extremely easy. This is extremely complicated, but this is extremely easy because the only thing you should do is compute the antiderivative of this. I want to call f and evaluate n between a and b. Okay, we know calculus, to say we know the rules to convert from this function to this function. I need to memorize a lot of. So fb minus f. Exactly the same we are doing in multi-dimension. So we never, this is the interpretation. The interpretation is the Riemann Sum. However, no, nobody doing using Riemann Sum. No. We compute the derivative, the antiderivative, sorry, and evaluate in between the points. Okay. So next time, Wednesday, we see how we extend this concept in multi-dimension. Okay? And we compute double integral first, and after triple integral. This is amazing. Okay, guys, so now focus in your test. Please try to do perfectly, explain me in detail step by step. So in the written test, I want details. Don't underestimate anything. Not like me, because somebody I skip algebra. No. You are doing perfectly. My recommendation is doing in the piece of paper, in one phase, you try to cover one question. You finish, no important that you have a space in blank, you go to the other phase, another question. Okay, organization extremely important. Everything is clear? Everyone is clear? Clear or confusing? Okay, see, Ernest. Okay, guys, so we finish. Okay, have a nice day. You have too many work. Remember, don't forget June 20. Also, the test and homework online. Have a nice day. Bye.